Sveiki visi. Hello everyone. Can you hear me? Can you hear me well? Yes, yes, yes. Hello, yes. Okay, nice to see you again. So today we're gonna continue in data analysis lecture. And again, we'll be sharing my whiteboard. Actually, I did tests and hopefully now everything will be recorded okay. Actually, I have succeeded in doing so. So hopefully you will get the full video now from the lecture and can follow it afterwards. Okay, so what we did actually so far, we have looked into a couple of topics. It was EDA, exploratory data analysis, and regression. So these two topics are almost over. We will be back from time to time to these topics as referring to for the examples, differences, etc. But mostly we will go into the different areas of data analysis and machine learning. And today we will start a new thing, which is one of the biggest things actually in machine learning and data analysis in general, and it is called a classification. Classification. Okay. I have to get used to this drawing board. Okay, so basically classification is a task that we will be looking at. It's a little bit different when the regression one, because now we have just very similarly, we have an input vector xi. Okay, so this is an input vector again, input vector. And we will be predicting y I hat, right, which is a output value, but this time it will be a discrete categorical class, right? So actually now our prediction will be for the categorical value, right? So categorical value. So what we will be looking at that the number of predicted classes or values will be k. K is the number of classes we're about to predict. Okay, so as an example, y I can be, for instance, now, which is very now it's from all the media, it is sick or not sick, hopefully, right? Sick or not sick, right? This might be two classes, right? Three classes can be good, average, or bad, right? So this is k equals 3, right? We can look into this as a some abstract values like ones or zeros and so on, right? So number of k is different in respects to the actual task. Okay, what comes for classification in general, we will be walking through it and we will look into the different aspects of it, but basically we will start from something which is called one thing, right? The first thing, which is called hard classification, and this is when a class is assigned 1 or 0, just like Boolean, right? So assign to class 1 or 0. And so basically each observation can be in some class or not in that class, right? So these are exclusive classes that an observation can be in. Classification could be so-called a soft classification, right? Then the assignment to class is made by probability. So basically that could be cases where 60% it's class 1 and 40% class 0. So basically classification could be either hard or either soft. We'll be looking into both of these cases. As well, classification could be the simplest case is so-called binary. Binary classification, when k equals 2. Number of classes is 2. 1 or 0, true or false, sick, not sick, and so on, right? And the second is multi-class. Multi-class classification, k is more than 2. We will look in both cases. But of course, what we will start from is the most simple case, because this is what we are usually doing. We're starting from something very simple. So we will look into the first case of hard classification, binary, something which is simple. So what we will be looking at right now is so-called linear classifier. Linear classifier, which is very similar to what we had in the linear regression, right? So basically now I'm drawing the space of x1, and here we had y, a predicted variable, right? Usually for examples, but right now we will have x2 as a second input variable. So basically, this is for simplicity. We're drawing two variables because this is simple to display. And we will have a couple of classes here. Let it be triangles like this, right? Triangles. And let it be circles, okay? These are two classes. So basically our predicted variable is coming from either a triangle or circle. This is the limited set of classes possible, and this is obviously two classes. Since this is two classes, we are looking at the binary classification task. And now, since we have two classes, we can find a line which basically separates these two classes. So our task is basically to find that line, right? So what we had for the line in regression, so far we looked into this multiple times, we had W0, right, as an intercept, plus W1, this is a slope, right, x1, equals, in this space, it would be equals x2, right? Okay, so we were basically looking at these two variables in order, we call them weights or regression coefficients, which we were optimizing our function upon, right? So right now we can do just exactly the same, but let's rewrite a little bit this function. So in linear classification, we just take this x2 and put it on the other side, right? Let's put it to the other side. So basically, let's put it here as well. So basically, we will have W0 plus W1 x1 plus, just let's turn up the sign, because anyway, we will be optimizing for the sign, right? So W2, we will have a weight for the x2 as well, because this is a variable which we are optimizing upon, and that's why we can just basically change the sign, right? So this becomes a better equation. And now, for instance, we can make it equal to 0, right? So basically, this means then this equation equals to 0. This means that our prediction is exactly on the line right here, right? So what it means that basically this prediction equals to 0. So once we get a prediction on the line, it is undecided. Either it's triangle, either it's circle. We just don't know. This function expresses that, right? And what we have for the binary classification, we have a plus side, +1. Then it is more than 0. These are the positive values of this equation, right? And these are the negative values of the equation, -1, right? So these are all the positive outcomes of this equation goes to top, and they are predicted as being triangles. All the negative guys are being predicted as circles because they are below the line. Okay. So basically, what we have here is simply the same like we had in linear regression function, but we can define our so-called the score function, right, which expressed in the continuous values range, right, because this is a equation that can be expressed in that range. So basically, let's name it a score. So our score equals to just the same function, but let's start from 1, W1, because we used to that when we introduced features, W2 x1 and plus W3 x2, right? And we can rewrite it into the same notation we used for the generic form, right? We have the sum, because this is a sum, I equals 1 until p, right? I equals 1 until p, w, oh, this is for j, sorry, this is j, wj, hj, and this is a feature, xi, right? So the score for each point is being computed by this exact function, right? Just like we had for linear regression in the generic form where we introduced the features, right? So this is a feature. And in the case of the intercept in the 2D space, right, we have W0 and the feature of J1 is actually 1, right? It returns 1, just like we had with the multiple regression generic form. Okay, and this equals to, in the matrix notation, weight vector, transpose, feature vector, and input vector, right? Just like we had before. And this is a score. And this score, since it goes into the continuous space, then it moves up, right? When it moves up from 0, then it's in the positive values range, right? We assume that this is a triangle. Then it is in the negative space, right? It goes -1, -2, etc. until -infinity. It is a circle. So what we need to quantize this, because what we are actually predicting, we are not predicting the continuous space, right? We're predicting a class. So for that reason, we need a quantizer, or so-called the activation function. So this is expressed so: if score more, let's make it equal to 0, right? If the score is more or equals to 0, then yi hat, right, we predicted values equal +1. So it is higher up, it's above the line, right? It's above the line. So with +1, we will be assuming that this is a triangle. And else we predict that this variable actually equals to -1. And we assume that this is a circle, right? Okay, so this is a quantizer or activation function. And how it looks geometrically. So geometrically, it looks like this. We have a line, the score, right? This is the score. It is a continuous space, a continuous value. We have 0 here, right? And this is our prediction. This is our predicted value. Okay, let me take some thicker line. Okay. So now, basically, then it goes from there. We assume that this is in minus. Here we don't know, right? We don't know, it's not zoomed, but we are just by the condition, we know that this is a plus side. Okay, so this is a -1. This is a 1. not minus, this is 1. Okay, so basically we just compute the score, and then based on sign, we decide where it goes, right? So later on, what we will be using, for simplicity, we will be using something like that. So our predicted value equals to sign of score, right? Sign of score with respect to W, weight vector, and xi, the input vector. I think it is clear, right? Okay. So now, basically, this simple approach, when we can separate two classes by the line, we just make up ourselves the line equation, and we make the quantizer so we can express into the binary problem, right? The continuous response from the score function, which is basically express in the binary classes, -1 or +1. Okay, so this actually is known very well, like the so-called perceptron classifier, which was implemented sometime in '57 by a guy called Rosenblatt. Okay, so there are various modifications. I will present you a couple of modifications for the perceptrons, but let me put in the algorithm itself. Okay, perceptron algorithm. Okay, for perceptron classifier. So basically, let's init weight vector, right? Let's init weight vector, which will be the first in the iteration, right? We init it to zeros. Let's make it all zeros, or a small random number. We can init to random numbers, some small random numbers, or init to zeros. It's all okay. So now let's loop for t equals 1. This is our iterator, right? T equals 1 until the number of epochs, and this is the hyperparameter, right? So we need to decide how many times we will loop. This is the hyperparameter alert, right? This is hyperparameter alert, because you need to make a decision how many loops you will be looping, because perceptron might not reach the best optimal solution, so basically might not converge. So basically you need to decide how many loops you will be going over your data set. Okay, so now for each xi, right, for each value in a data set, in your data set do, right? So we will be looping for all the values in the data set. Okay, so what we do right now is basically we predict the outcome, right? So by using this sign function, right? Sign function, we are predicting of WT transpose H xi, right? So we basically sum up products of weights and features, right? And now we just basically loop for j equals 1 until p, right, do. Okay, so now we basically loop over all the dimensions, all the input vector elements, right? And now let's update the weights. T plus 1, right? equals wjt with previous weight, right? Previous weight plus eta, which is again hyperparameter, a hyperparameter alert, right? Hyperparameter alert. And what we do, we just basically take the difference between what is the actual class, right? So actual class, right? Actual class, and this is a predicted class, right? And this is a predicted class. So we take the difference, right? We take the difference. And as you know, the actual class is either 1 or -1. So predicted class is 1, either -1 as well. And this is a feature, right? Okay, so let's go through some examples. So the generic form of the gradient for weight j, again, just to repeat it, there is a learning rate. Okay, there is an alert actually, not hyperparameter alert, but alert on my mobile phone. Okay, so just repeating the same what I did before in the generic form, right? Like a gradient with difference, which we need to apply to the current value. So basically the difference between the predicted and the actual class and the feature magnitude, right? Feature magnitude. Okay, so this is a generic gradient in some space. We will come up to this pretty soon. I just want to show you some example now, how it would actually work. So let's go through a few examples. This perceptron algorithm. Okay, so let's make it up that, for instance, we have yi, the actual class is -1, and yi, the predicted class, equals -1 as well. So everything is fine, right? So then, okay, let me put it like this. So under these conditions, what we have is the gradient of wj, right, equals eta. So we have -1 minus -1, right? And this is the feature, right? This is the feature. So -1 minus -1 canceled it out, it becomes 0, right? So it's 0. So basically, if we have the correct situation, if the class is okay, we do not need to do any move with respect to this point. Now let's do again example with the positive classes, both positive, right? So both positive classes, then our gradient is 1 minus 1, right? Hj xi, and again we have 0. So this means that these two cases are all okay. No change. No change required, right? Okay, so if not correct, so for example, we have -1, one case, and we predicted value, right? And we predict that it was for instance, a triangle, but we predict it to be a circle, right? So what we do now is that we calculate the weight as being -1 minus 1, right? Hj xi, and this is equal -1 minus 1, right? So this is -2 eta Hj xi, right? So it has to change, right? This you can consider as being constant, and this actually expresses the feature is expresses the magnitude of change, right? And this is basically a learning rate. Okay, and another example. So 1, and this was yi we predicted equals -1. Right, so we have again the situation. So now it was 1 minus -1, right? Hj xi, all the same. So now 1 minus -1, this is 2. So it moves to the positive side, right? It moves to the different direction, because this was, we have predicted the positive value, right? And it has to be -1, so we moved to the negative side, right? This is a positive class, but we predicted it to be negative, so it has to move to the positive side, into the direction where actually the line is expected to be, right? So this implies the direction of move, actually learning rate plus direction, right? Direction. Okay, this is a very important thing to be moving into the right direction of the gradient itself. Okay, so now some more examples for your convenience. Yi equals +1, right? And the predicted value equals to -1, and the feature hj xi equals to 0.5, for instance, right? So then our gradient, right? Our gradient equals eta 1 minus -1 times 0.5, and it equals to 2 times 0.5, it's eta. Right, so it's basically, if you have the feature 0.5, then you move by eta, right? This is positive guy. So now let's assume we have the same situation here, right? The same situation, but the feature is a little bit different. So it's, for instance, 2, right? So the gradient equals eta 1 minus -1 and 2. So it actually moves by 4 eta, right? So the different magnitude. So this is a different magnitude of move, right? So basically feature determines the magnitude of the actual move. And then the other guys define the learning rate, how much to move. So eta basically something like a small number. So we are moving by the small steps. And the sign actually defines the direction of the move. So something simple, something familiar you already have seen in regression, but this actually applies to the perceptron learning algorithm, right, with the quantizer. Okay, should not be moving this. Okay, and actually it learns. Okay, so perceptron can be applied for the tasks, and the convergence is guaranteed if classes are linearly separable, right? So just for example, like just we saw before, if we have triangles and circles, right, and there's a line, any line, right? I can draw many infinitive actually number of lines that can separate these two classes, but if it is separable by the line, so perceptron can solve, right? Can solve. And you actually can loop this algorithm until you meet the convergence, until no changes, until the gradient becomes 0, right? Cumulative gradient becomes just 0. Okay, and you can move until that. So now situations, slightly different, for instance, when you have the triangles and circles mixed a little bit between them, right? So this kind of situation is not linear separable, but perceptron would find a solution to you, but it cannot solve it, right? It cannot solve, so you must rely on the number of, so this can solve, can converge, right? Can converge, cannot solve, cannot converge, and you need to rely on the number of epochs. So basically you can loop, but it will never stop. It will always be jumping, right? If you would wait for the gradient to be 0, it will not. It will always be jumping around. So because of this situation, you have to define some number of epochs, so your algorithm would stop here. And obviously, we can have even more sophisticated situations that are completely not solvable. So for instance, situations like this, when we have triangles and we have circles around, right? So this is completely not solvable, cannot solve, right? And of course, number of epochs. But for your interest, I can tell you that this kind of problem can be solved with some data transformation. So for instance, what we could do in order to solve this with perceptron is to transform this guy into the polar coordinates. So basically, this is an example for you how we can solve situations like this if you encounter. So basically, you can do two things: center data, and the second thing is to use the polar coordinate system, right? So what it would mean, basically, it would mean that you would transform your data before actually applying the perceptron algorithm. So your center would be somewhere here, right, at the center of the data, right? Just like we had with normalization, right? And then once you recentered your data, you can basically take the angle of the data points, right? So the angle would be going to this direction until pi. This is a half pi, right? From trigonometry, you should know. Half pi and pi, this is 0. And this is moving to a different direction. This is minus a half pi. And this is minus pi, right? So basically, this would be expressed, the angle would be expressed here on this axis. It will be pi, and this is minus pi, right? And here would be an r. This is a length, this is a distance from the center, right? This is a distance from the center. So basically, this kind of situation can be transformed into the situation where your triangles would be somewhere here, right? So we have 1, 2, 3 triangles on top, and we have 1, 2, 3 triangles on the bottom. 1, 2, 3, right? Triangles on the bottom, and all the circles are around it. 1, 2, 3, 4, 5, 6, right? And they're further away from the center. 1, 2, 3, 4, 5, 6. And this one, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, it should not be going away. Okay, this is the wrong example. It should not be over pi, right? So it should be inside the pi. Okay. So now, once we did the transformation like this, it is this data set is linearly separable. Okay, this is just an example for you that you can imply various transformations for your data set, and then after the transformation, hopefully your data set becomes linearly separable. So you have to look in your data in a very creative way. Use your imagination, and possibly you can do the transformation where you can solve this situation. Okay, so now I would like to draw you the scheme of the perceptron so you can have a better understanding how it works. because this is actually a single neural network, which we'll be covering at the end of the course. But for your convenience, I'm just basically drawing the scheme of this of the perceptron algorithm. So basically, what we have here is we have yi, right? This is our actual class again. Actual class. When we have, usually we need for the classical perceptron, we need a intercept. We need to include intercept. This is 1, right? And now xi1, xi2, and so on until xi, let's make d. So these are not features, these are dimensions that are coming right from the data set, right? So this is our input vector, right? xi. Okay, so we have this input guy and we know the actual class, right, which we want to predict. So we can do the learning. So basically with each of these input vector elements, right, we have associated weights W0, W1, W2, and WD, right? So we have weights associated with each of these input vector elements. And now we take products of these guys, right? We take products of these guys, and what we do, we sum it up, right? We sum it up. So this is our summator. Right? Summator or net input function, etc. Because it takes multiple inputs, take products. Each input is basically multiplied by the weight, and when everything is being summed up, then we have a so-called activation function. Which in our case is sine or quantizer, because it takes a continuous input and it converts into 1 or -1, right? It basically creates a quantum out of the continuous input. Okay, so this is a quantizer. And so after the quantizer, we have our predicted value, right? So this is the prediction. So before doing the actual prediction, we need to learn. And learning is made by using the error, right? Error box. So we take that prediction value, right? Inject into this box. We take that guy, so we know the difference if they're the same, if we have predicted correctly or not correctly. We make a prediction, right? And then if not, we just apply new weights, right? So basically, weight update. And we basically loop all the time. So this is a perceptron algorithm. Okay, this is a perceptron algorithm I wanted you to show, the simplest one, algorithm for classification. Okay, so slight modification of this perceptron algorithm. I will copy that guy. Okay, let's try new technologies. Okay, I'm copying this guy up. Okay, so this is copy. Okay, now I need to paste somehow. Okay, I'll just paste it. Okay, I will apply a small modification for the different algorithm, right? So I want to the previous one not to delete, but to keep it up. Okay, I'm just putting side to side. Okay, more or less. So basically, what I want to do is small modification. There are cases when activation function is used so-called linear. So basically, activation function, we will not use the sign, the quantizer. Okay, I will basically delete that guy here inside the box. And this is a so-called a linear activation function. Linear activation function. Okay, so this is nothing. It actually is being done. This is just exactly the same value, right? The continuous value is being taken and injected in the error function, right? Exactly the same value. The quantizing is still needed, and it's actually being performed just before the prediction of the class. Okay, so let me put it here. The actual quantizer is made over here just when we want to use the class. Okay, here it is. So this is the quantizer now. Okay, so this kind of algorithm where we use the continuous value, right? It is a slight modification of the perceptron, is called, for you to remember, an adaptive linear neuron, or an algorithm Adeline. Okay, so this is a small modification where we don't quantize when calculating error, but we use directly the output of the score function. It is again has a sign plus or minus, but it is used directly in the calculations. We will not go into the details of this, but just a slight modification. And now we will go into the modifications of that, and I will introduce you the probabilities. So basically, this was binary classifier, a hard classifier, because it assigned to the class -1 or 1, right? This is very simple. You can implement this without, I guess, any problems. Loop it up for the some defined set of epochs, and try to achieve the separation of the classes. Okay, so that's it for the hard linear classifier for now, and we will be moving into the probabilities. I will start a new whiteboard here. Okay, so now assignment, hard assignment, not always good, and usually is not that good, because we want to know how much the observation actually belongs to one or the other class. We want to have some evaluation, the probability of being in that class or the other. So basically, this brings me into the express class, very fast explanation of the probabilities. So basically, let me talk about this right now. So probabilities. Okay, so some introduction into the probabilities. So basically, we will be using notation of capital P. This is a probability, right? A probability that the class is actually +1, right? This is probability of being in a class positive, in a positive class, right? And this comes from the range. The probability is coming from the range from 0 to 1, right? From 0 to 1. This is a range of values that probability falls into. right? So we can write it down with probability of y equals some class is actually less, more or equal to 0 and less or equal to 1, right? From this, within this range. Okay, so as well we can write the same thing, that probability of being in the negative class is just exactly from the same range, right? Okay, and the sum of probabilities, right? Probability of being in the plus class plus probability in being in the negative class is equals to 1. Right, so the sum of all the possible probabilities is actually equal to 1. So we can extend that, and in multi-class classification, right, equals to A plus probability of Y equals to B, probability of P, Y equals to C equals to 1. If Y, the only classes that it could take is actually A, B, or C, right? So being one of these classes, the observation being was one of these classes, all the probabilities sum up to 1. Okay? So we can even extend that to summing up, like, for instance, this as the sum of J equals 1 until K, the number of classes. This is the probability of Y being J, right? And all the sum of these probabilities of until K is actually equals to 1. Okay, these are simple things, I think, but we need to move on. And the conditional probability extends a little bit the notion and the definition of probability, that we have a probability of being in a class plus 1, for instance, right? Given xi, right? So this is a, let me explain you, let me write down this notation. So this is a probability. Okay. Probability. This is an output. Okay, so this is a class. So probability that output is in this class. This means given, and this is given with input, right? Input. Okay, so what we will be looking at is actually finding, our task will be to find the probability that given input vector, right, the class is plus 1. So what is the probability for that? So everything else actually applies, what we've seen so far. So for instance, we can write it down that the probability of being in a class given something is actually in between the range from 0 to 1, right? So all these previously specified notations and rules actually apply. Plus 1 given xi, right? It is less or equal to 1. It falls into this interval, right? So again, all the classes can sum up, right? So basically, let me write it down, equals plus 1 given xi plus probability y equals minus 1, right? Given xi equals to 1. Okay, so if we have a binary classification, so this is binary classification problem. Okay, in contrary, if we have a sum of I equals 1 until n, so for all the observations, right, the probability of y equals plus 1 given xi, right, so sum of all the probabilities for all the vectors being in some class does not equal to 1. It equals to something else, obviously, right? So it does not need to be mixed, because what we are talking about just the classes, right? So classes is for the single observation, right? So number of classes is k. So probabilities of y being in the class J, given the observation equals to 1. Okay, I think this is clear, right? I think these are simple things, and you can use to this. Okay, so conditional probabilities, we have just a simple probabilities that some event actually occurs, right? So we need to find out, because we want to predict what is the probability for the observation being in one of the classes, right? So now this is a conditional probability that we have an input vector. We will have later on weights, because for the given weights we will have a certain probabilities, and we will be looking at the better set of weights. Okay, so we can solve now for the binary classification problem, right? So let me put it here. For the binary classification problem, the quantizer, right? The quantizer will be such that if the probability of y being in +1 class, right, given xi vector is more or equal 0.5, right? Because our probabilities are vary from range 0 to 1, right? And the probabilities for all the classes actually sum up to 1. So we expect that for the binary classification problem, if the probability of being in class +1 more or equal to 0.5, this is an average, right? Then we think that yi equals +1, right? Or else yi, or else, because 1 minus this probability is actually a probability of being in a negative class, right? So else is here. So this is again the binary classification problem, right? This is for binary classification problem. Otherwise, we should be looking for a multi-class classification problem. We will be looking into the highest probability. They would be divided in the in sum of all the probabilities for the different classes would be summing up to 1, but we should be looking into the highest probability of being in a certain class. So then we should put this into the right class, right? The highest probability means being in that class. Okay, so this was the introduction into the probabilities. Anything else I need to say? Let me check. I think so far so good. Okay. Okay, let's move on. So what we will be doing right now is actually we need a so-called link function, because what we have is the score so far we had, right? The score, just to remember for you, we were calculating the linear score, WT, weight vector multiplied by the feature vector, right? Multiplied by the feature vector. And values were moving in the space between minus infinity to plus infinity, right? And the uncertainty was around 0, right? So in order to transform this score into the probabilities, we need to have something like, so for instance, the probability of y being in a plus class, right, given xi, we need to have the j, right, some kind of a function j, which would take the score hxi, right, which would take the score from minus infinity to plus infinity and transform it into the limited space between 0 and 1, because this is where probabilities lie in. And it was 0 right here. So here we need to be 0.5, right? So we need to find out this length function, right? To express our score, which we calculated in the space of unlimited bounds, right, into the bounded function where we would have from 0 to 1, which is what probabilities are for. And okay, so this length function in our case is the logistic function, right, or the sigmoid, or logit. So there are various names for the function, right? So the sigmoid, we can put it as sigma, right, where we will provide a score, right? So basically this is exactly, we're providing a score as an argument, right? And it equals 1 divided by 1 plus e minus score times minus score. Okay, so this is a function we will be using a lot, because what it does, it links from the space of continuous values into the limited space of probabilities. So what it actually does, it takes, let's just draw the graph now graphically. So what it does actually, it takes from, for instance, space of let me put like this, right? So this is 0, this is, let's call 6, this is minus 6, okay? 6 and minus 6, and this is the score of xi. So it's moving from minus infinity into plus infinity. This is just some bounds around 6, right? Because around 6, the classical function just lays down. Okay, and what we have here is on this axis, let me put it like that, we will have a sigma of score xi, right? Okay, and here we have 1, here is 0.5. So basically this function, when we plug in the score into the sigmoid goes something like this. I will try to do my best, not promise. Okay, so it goes like that, right? The more it goes to the negative side, the closer it's to 0, right, to 0 probability. Then it reaches 0, the score, right? It is exactly 0.5. Right, so probability is uncertain, right? It's right on the edge. And when it goes to the plus side, the farther it goes to the plus side, the more it is closer to 1. Okay, so this is the function, right? Let me make it a bit thicker. Okay, so this is like that. I'm not a good drawer here, but anyway, you can get an idea how the sigmoid function looks like. Okay, so basically now we can plug these guys in, right, and show it up the complete state, the complete function. So probability of y being a plus class, right, given xi and w, this is an input vector and these are the weights at the current state, right, equals 1 divided by 1 plus e times minus w transpose h xi. Okay, so this is a probability of being in a plus class. All right, so basically we can have in here, I will put a small table, score of xi, just for the better understanding. This is a probability of y being on a plus class given xi w. All right, so let's make a small table just for the illustration. So then we have the score minus 6, right? So probability of being in the plus class is 0.0025, right? So this is very, very tiny probability of being in that class, okay? In a positive class. Minus 4, it is 0.02. I just calculated that. Minus 2, if it minus 2 the score, then we have 0.12, right? Then we have 0, so obviously we will have 0.5, right? So right in the middle. So again, then we have a 2, we just move into the positive side, the probability is 0.88, quite big. 1, then we have 4, probability of 0.98, right, and 6, and just for this symmetricity. Oh, sorry. Sorry, I just got a call in the Skype. Okay. So, and 0.997. Okay, so just gives you an example how the actual score which we have calculated by using the continuous function, a linear function, actually changes by the link function, right? By the link, by the sigmoid. Okay, so basically what happens now is that by using weights, so the intercept W0, how it actually affects, right? How it actually affects the sigmoid function. So then W0, the intercept equals to 0, right? We have the change right on the 0 axis, right? So nothing actually changes, and we have a classical sigmoid function, right? So it moves right here and right here. When W0, the intercept equals to 0, right? Then the intercept W0 equals 2, right? So this guy goes into a 2 range, right? So basically the function moves by 2 on a side, right? So basically it moves by 2. So the position of the sigmoid function is actually defined by intercept, right? So basically intercept defines where we put that function on this axis, right? So basically this is the position that's defined. So now in the binary classification problem, then we have a weight W1, so this is an intercept, right? Intercept. how intercept actually affects. So it affects where the line actually goes in, right? So here we might have a change at around -2, right? So this is -1. So W0 equals -2, right? So basically intercept defines the position, right? The position of this curve. All right. So, and what does the slope do for the intercept function? It changes the slope just like it did before, right? So then the slope equals to 1, right? When the slope equals to 1, let's do a slope like this. So W1 equals to 1. So it is a classical example. So let's put it like this: W0 equals to 0 and W1 equals to 1. And these are the conditions when these values apply, right? So when we change the W1, the slope, to something else, right, it becomes either steeper, right? So for instance, it can become steeper, the function, right? So this would be W1 equals to, for instance, whatever, 3, right? Then it becomes higher up, right? This function becomes steeper. Basically, the change of probabilities becomes much narrower in terms of the score, right? So this is again score, this is score, and this is a probability, right? This is a probability. And then the intercept becomes, the slope becomes less than 0, right? It becomes less than 1. So basically this flattens out, right? This flattens out and the range becomes much wider, right? So this one basically W1 equals to 0.3, something like this. So basically, by applying weights, by learning weights, we basically are moving in a space, right? This curve, between the binary classes, right? We are moving along the axis, as well as we define the slope, how wide it is or narrow, right? So basically, by learning weights, we change this curve, how it's actually laid down in the space. So basically, this is basically the range, the probability of being in a plus class, right? So Py equals the +1, right? And the further and it closer to 0, so this is probability of being on a negative, right, class. Okay, and this function basically defines where and how fast do we change the probabilities, right? So this is again the same thing, probability of being in the positive class or probability in being in a negative class. Okay. Okay, so basically, I think that I have explained today everything I wanted. Not actually to the end, but don't want to get into the logistic regression, because this logistic function implies that we can learn these weights by using this logistic notion of probabilities. And I think we will not start because it would take us another hour. I don't want to continue. So basically next week we will look into the logistic regression for classification. And this is basically will be our work with this logistic function. and learning weights, and that basically will put the function on this space, and we will be defining the location as well as the slope in binary classification. Okay, so I don't think that I will continue. I think I will stop here unless you have questions. If not, then we can close the lecture. Okay, just stop recording, and we will continue next week. Thanks for joining. I will put up whiteboard sketches